Running circles around circles lab.
Question 1. A hypocycloid is a curve traced out by a fixed point P on a circle C of radius B as C rolls on the inside of a circle with center O and radius A. Show that if the initial position of P is A0 and the parameter theta is chosen as in the figure, then parametric equations of the hypocycloid are as follows. In order to find point P, you need to have a basic drawing. You need to draw a circle with center O and a line going from that center to the outside of the circle. From there, you can place a point P on the graph and make a circle inside of the bigger circle, with the center of that being Z and the radius being B. So in order to find P, you need to find its X value and its Y value. In order to do that, you're going to create a right triangle from here to here, and you're going to label those as ZX and ZY. Using ZX and ZY, you can make the equations using basic trigonometry that cosine theta equals QX over A minus B, and sine theta equals QY over A minus B. Next, we want to find the distance between ZX and X, and ZY and Y. So we draw another right triangle here with angle 2 theta and point W. The distance in between ZX and X will be QS, and the distance between here will be SP. Therefore, in order to find X value of P, we can add ZX and ZW, and to find Y, we can subtract WP from ZY. Due to similar angles identity, we can define this as theta, and because this line and this line are parallel, we can decipher this to also be the angle of theta. From there, we can use arc length in order to determine what A and all the other values will be equal to. In order to find arc length, you need to do radius times length. So here, it would be A theta would be the arc length. And we can see that it would be the same thing inside because the radius here is still A and the angle is still theta. The only difference here being that the angle is theta plus theta 2. Because of that, we can derive the equations that A theta equals the radius B times, in parentheses, theta plus theta 2. Using some basic calculations, we can derive that the eventual theta 2 will be equal to theta times A minus B over B. From there, as previously stated, we can say that the X length will be ZX plus ZW, and the Y length will be ZY minus WP. Basically, because of the new found theta 2 value, we can use, again, cosine and sine equations to define what ZY, ZX, ZW, and ZP would be. Using, again, trigonometry, we can determine that ZY will equal A minus B times sine theta, ZX will equal A minus B times cosine theta, ZW will equal the radius B times cosine A minus B over B theta, and WP will equal B, the radius B times sine A minus B over theta.
Number 2 for our lab, call for us to graph the hypocycloid with A being a positive integer and B always being 1. The equation found in question 1 was used to graph these scenarios. First thing we discovered was that A had a direct correlation to the amount of cusps that were formed in the graph. For example, when A had a value of 10, the resulting graph would form a shape with 10 cusps. It was also discovered that if A was an even number, such as 4 or 10, then the graph would contain 2 planes of symmetry. The planes of symmetry run along the x-axis and the y-axis. However, we also found that if the value of A turned out to be an odd number such as 5, there would be only one plane of symmetry, and the x-axis here would act as that plane of symmetry instead of the y-axis. Now, When A was equal to 1, the graph would have 2 planes of symmetry and 4 cusps. The question also asks us to find the reduced equation when A equals 4. Using trig identities, we found that the simplification of x from 3 cosine theta plus cosine 3 theta would be equivalent to 4 cosine cubed theta. Now, the same would be found using trig identities for y. Y was 3 sine theta minus sine 3 theta. Using trig identities, it would simplify down to 4 sine cubed theta.
Part 3 of the lab asks for you to find out what happens when a equals a fraction and b equals 1. For the fraction, the numerator and denominator must have no common factor. Part 1. When the numerator equals 1 and the denominator is varied. For this, we performed a variety of tests. First, we found when d equals 2 and theta ranges from negative 2 pi to 2 pi, the graph resembled a sideways heart/cardioid. Likewise, when d equals 3 and theta range from negative 2 pi to 2 pi, the graph is still the same with the cardioid. However, extra loops have formed on the left. This stayed the same for when d equals 4 and theta ranged from negative 2 pi to 2 pi. Notice how the cardioid shrinks every time and the loops start growing. When theta is increased from negative 2 pi to 2 pi to then being negative 10 pi to 10 pi, we see full loops form. In this example, d equals 3. Here, d equals 4, and here, d equals 5. The range of theta does not necessarily have to be negative 10 pi to 10 pi. In fact, it should only have to be what is equal to d. So negative 4 pi to 4 pi would show the full loops here. However, negative 10 pi was easier for the graph. What you can notice is every time d increases, the size of the cardioid becomes smaller, and more loops are added. Part 2 of question 3 asks about when the denominator is held constant and n is varied. Here, the denominator is kept at 3 for all 3 images. First, n equals 5. As you can see, a 5-pointed star is formed. When n equals 7, a 7-pointed star is formed. And when n equals 8, an 8-pointed star is formed. To summarize, when the denominator is kept the same and n is changed, the shape form will be a star with n number of points. Part 3 talks about when the numerator is d plus 1. Here we see a shape with n equals 3 and d equals 2. Here n equals 4 and d equals 3, and here n equals 5 and d equals 4. Essentially, the same shape this is the same as the regular hypocycloid. The only difference is that these are slightly smaller than normal.
Number 4 for our lab barred the question as to what would happen if b stayed 1 but a became an irrational number. We explored this question using radical 2, radical 7, and e minus 2. When the values of radical 7 and 2 were used, the graph displayed a strong overlap of multiple cusp shapes, like so, with the formation of some sort of oval in the middle. The shape seemed to resemble a pizzelle cookie, and as the radical became larger, the more defined the central oval would become. Also, the increase in the size of the radical caused the immediate surrounding area to the oval to become more dense and darker, as compared here, radical 7 and radical 2. The increase in theta also caused a visual difference in the resulting graph. If theta was doubled, such as here, then the surrounding oval would be twice as dense than a graph with a normal theta value. And if theta was quadrupled, such as here, then the surrounding oval would be 4 times as dense and quite larger. So we can determine that as theta reaches all real numbers, then the overall shape would resemble a standard donut, with a perfect oval in the middle and the surrounding graph being completely shaded in. Another irrational value we used was e minus 2, and when e minus 2 was used, the graph became inverted in cusps as compared to the radical graphs, with the cusps pointing inwards. Also, in this example, if theta was increased by any side, in this case quadrupled, the amount of lines and lattice structure would also increase. Compare this graph to this graph here. Furthermore, the density of the line points furthest out from the center would also increase. This is a direct clash with what was found with the radical points, where the density was found starting on the inside and increasing outwards, where this was starting on the outside and increasing inwards.
Question 5 is very similar to question 1, except in this case, the circle is on the outside instead of being on the inside. This is called an epicycloid compared to a hypocycloid. Much of the work is the same. For this large circle, you must draw out a radius going from here all the way to the middle of this one. Now, we know that the radius of this line right here of the large circle is A, and the radius of the small circle is B. The angle of this is theta. If you draw a line from the middle of the small circle down to the x-axis, you'll find that the hypotenuse of the triangle formed is A plus B. The radius of the large circle plus the small circle. The length from the center here to this point made by the small circle is Zx. And this would be Zy. Using these and trig, we can find that the Zy will be equal to A plus B sine of theta, and Zx is A plus B cosine of theta. Now that we have these, we need to do the same as we did in number 1, and add in a line segment for this length and subtract a line segment for this length. To do that, we must form a small triangle in the middle, as in we did for the first question. This will have a theta of theta 3. You might be wondering where theta 2 is, but we'll get back to that. For this triangle, we have a length from Z to W, and then we have a length from W to P. These are what we will be using in our trig. So the sine of theta 3 is WP over B, as B is the radius and also the hypotenuse of the small circle. Cosine will be ZW over B. Using these, we can find that WP is B sine of theta 3, and ZW is B cosine of theta 3. Now, in order to find out what theta 3 is, so that we can substitute it in our final equation, we must use theta 2. The arc length of this right here is A theta, and this is also the distance that P has moved, and therefore that this arc length here will equal. So this arc and this arc are equal as they are both A theta. But this arc length is also the radius of the small circle times this angle right here, which is theta 2. So A theta is equal to theta 2b, as you can see right here. Simplifying, we get that theta 2 is A over B theta. Now, what we can do with that is figure out that theta 3 plus theta 2 plus theta, as this angle and this angle are like angles, is equal to pi. Knowing that they're equal to pi, or 180 degrees, we can simplify to find that theta 3 is pi minus theta A plus B over B. Finally, knowing this information, we can use simplification to find our final equations of x equals A plus B cosine of theta plus B cosine of pi minus theta A plus B over B, and y equals A plus B sine of theta minus B sine of pi minus theta A plus B over B.
Question 6. Investigate the possible shapes for an epicycloid. Use methods similar to problems 2, 3, and 4. Part 1. Effects of an epicycloid when b equals 1 and a is a whole number. When a equals 1 and b equals 1, the epicycloid looks like a sideways cardioid. However, when a equals 2, an epicycloid is forming that has two bumps, one on top and one below. When a equals 3, something similar happens and another bump is formed. Following the pattern, when a equals 4, you get a fourth bump. Overall, you can conclude that when a is a whole number and b is 1, a correlates to the number of bumps or clubs if you're looking at it as if it's a four-leaf clover, And when A equals an even number, you can see that it has two planes of symmetry, one across the x and another across the y. However, when it's odd, such as when A equals 3, you can see that there's a plane of symmetry across the x-axis, but not one across the y-axis. Question 6, part 2, fractional values of A. Keeping n as 1 and changing the values of d. For the first example, when n equals 1 and d equals 2, a corridor is formed and a loop is formed around it. For the next example, when a equals 1 and d equals 3, we can see that the choroid and its loop still remains. However, there is another loop on the outside of it. Furthermore, you can see that even though the size of the outermost circle is the same, its contents within are condensed as we continue. This pattern can be seen even more on display when n equals 1 and d equals 4, where the cardioid is much smaller than its original, yet the outermost circle is the exact same size. So therefore, we can conclude that when a equals n over d and n equals 1, a cardioid is formed in which d will be equal to the amount of loops plus the cardioid in the graph, and that the outermost circle of the cardioid will always be the same length, while the higher the value of d is, the more condensed the inner contents will be. Furthermore, it should be noted that in order to see the full loop shaped, the range of theta may need to be increased as d also increases. Question 6, part 2b. As the denominator stays constant and n changes. When d equals 3 and n equals 5, we can see that a circle is formed with a certain amount of petals on the inside and inner loops connecting it. As you increase the value of n, you can see that the number of petals inside increases. For example, when a equals 5, there are 5 petals, and when a equals 7, there are 7 petals on the inside. Furthermore, you can see that as the value of n increases, the amount of lines between the petals and the outermost circle also increases. Question 6, part 2c. When n equals d plus 1. In our first example, we can see that n equals 6 and d equals 5. It forms a very similar shape and follows a similar pattern as the previous example, where d is constant. The difference being that as d and n both increase in intricacy, the number of petals, 1 increases, according to n, as when n is 8, there will be 8 petals on the inside, and d equals 7, you can see the intricacy between the petals and the outer circle increases. That pattern can be further expanded upon when d equals 9, and you can see that it is even more crowded and more dense between the petals and the outermost circle. Another thing to note that the outside or outermost circle is approximately the exact same diameter, no matter how high the n or d go.
Number 6, part 3, takes a similar approach to number 4, and it asks what would happen if the epicycloid graph had an irrational number for a. We found that as the radical values increased, such as from radical 2 to radical 7, then there would be more petals between both graphs here and here. There's an increase of petals here from here. Also, the graph lines, as radicals would increase, would also become more in line with each other and more intricate as the radicals increased. Additionally, when e minus 2 is used as the irrational value, the graph appears inverted in comparison to the radical. Also, the central shape is a 5-star pattern. When theta increases, for example, theta is doubled here, the surrounding line lattices multiply. Also, the graph becomes more dense from the outer region going inward. So the outer part of this graph is more dense, and as theta increases, the density will increase towards the middle. Number 4 also demonstrated a similar shading pattern from inside to outside when e minus 2 was used as the irrational value.